Welcome back to G Fun Facts Online. Today we are turning our gaze 93 million miles outward toward the engine that drives our solar system. We are going to talk about the sun, but not the static yellow disk you see in the sky. We are talking about the roaring beast of magnetized plasma that defines our existence, and specifically, a ghost in the machine that has baffled physicists for over 60 years. We are going to explore the Coronal Diagnostic Experiment, or CODEX, a mission that launched in November 2024 to solve the mystery of the solar wind. Let's start with the fundamental problem. The laws of thermodynamics as we understand them in our daily lives are fairly straightforward. If you have a heat source like a campfire and you walk away from it, the air gets cooler. If you release a gas into a vacuum, it expands, and as it expands, it cools down and loses energy. This is basic physics. But the sun does not follow these rules. The surface of the sun, the photosphere, is a blistering 6,000 degrees Celsius. But if you move upward into the sun's atmosphere, the temperature doesn't drop. It skyrockets. A few thousand kilometers up, the temperature leaps to over 1 million degrees Kelvin. This superheated plasma forms the corona, the faint halo you see during a total solar eclipse. And it gets stranger. As this plasma flows outward to become the solar wind, it doesn't slow down. It accelerates. By the time this wind passes Earth, it is moving at 1 million miles per hour. So, somewhere between the surface of the sun and a distance of about 4 million miles out, a hidden engine kicks in. Energy is being dumped into the plasma, heating it up and hurling it outward against the pull of gravity. This region is called the acceleration zone, and for the entire history of the space age, it has been a blind spot. We have touched the wind near Earth with satellites, and we have even flown through the outer corona with the Parker Solar Probe, but we have never been able to see the mechanism of acceleration as it happens. We know the wind exists, but we don't know how it works. This is where CODEX comes in. To understand why CODEX is such a massive leap forward, we have to look at the two competing theories that have divided astrophysicists for decades. Theory number one is called wave turbulence. Imagine the sun as a pot of water on a stove. The magnetic field lines rooted in the churning surface are shaken like guitar strings. These waves travel up into the corona. When they collide and tangle, they create turbulence, cascading energy down to smaller scales until it dissipates as heat. It's a slow burn, a steady heating process. Theory number two is interchange reconnection. This is much more violent. It suggests that magnetic loops, arches of plasma, collide with open magnetic field lines. When they touch, they snap into a new configuration, like a rubber band breaking. This releases an explosive burst of hot plasma. Here is the catch. Both theories can create a solar wind. To figure out which one is right, you cannot just measure the speed of the wind. You need to know its history. You need to answer two questions simultaneously. Was the gas hot before it started moving fast? Or did it get hot and fast at the exact same moment? The first suggests waves. The second suggests reconnection. To answer this, you need to measure temperature and velocity at the same time, in the same place. And until now, we couldn't do that. Traditional coronagraphs, telescopes that block the sun to see the corona, could only measure density. They could see how bright the gas was, effectively counting electrons, but they couldn't take the temperature, and they couldn't measure the flow speed of the gas itself, only the speed of clumps drifting within it. CODEX is the first instrument designed to break this deadlock. It is currently mounted on the International Space Station, having been installed on the Express logistics carrier in late 2024. It is a collaboration between NASA Goddard and the Korea Astronomy and Space Science Institute, or KASI. CODEX is essentially a technological scalpel designed to slice into the solar wind's formation zone from about 3 to 10 solar radii out. The way CODEX works is a masterclass in optical physics. First, it has to block the sun. The sun is 1 million times brighter than the corona. Trying to look at the corona next to the sun is like trying to see a firefly hovering next to a searchlight. CODEX uses a multi-stage system to kill stray light. It has an external occulter to block the main disk, an internal occulter to block the residual glare, and a specialized focal mask that acts as a trap for diffracted light. But the real magic lies in how it extracts data. It uses a method called the filter ratio technique, based on theories developed by L.E. Cram in 1976 and Nelson Reginald in 2001. Let's break down the science of this technique because it is fascinating. The light from the sun's surface is not a smooth rainbow. It is crossed by dark lines called Fraunhofer lines, which are caused by cooler atoms absorbing specific colors. When this sunlight hits the hot electrons in the corona, it gets scattered. This is called Thomson scattering. Now imagine a tennis ball machine firing balls at a wall. If the wall is still, the balls bounce back at the same speed, but the electrons in the corona are not still. They are zipping around at millions of degrees. When the photons hit these fast-moving electrons, they get a kick. Some come back faster and bluer, some come back slower and redder. This thermal motion smears out those sharp Fraunhofer lines. A deep, narrow, dark line in the spectrum becomes a shallow, broad dip. The hotter the electrons, the more smeared the spectrum becomes. CODEX takes images through two very specific filters. One is centered right inside a spectral dip, specifically near the calcium H and K lines around 393 nanometers. The other filter looks at the continuum, the smooth part of the spectrum. By comparing the brightness through these two filters, CODEX can calculate exactly how much the line has been smeared. That gives us the electron temperature directly. But what about velocity? This is where the Doppler effect comes in. If the entire cloud of gas is flowing away from the sun, the whole spectrum shifts toward the red. Measuring this shift is incredibly hard because the lines are already so blurry from the heat. It's like trying to see if a fuzzy cloud has moved an inch to the left. However, the scientist Nelson Reginald showed that while the shape of the spectrum is dominated by temperature, the ratio of intensities at the red wing and the blue wing of the spectrum changes very sensitively with speed. CODEX uses another set of filters to sample these wings. By combining these measurements, the instrument can isolate the radial flow velocity. So for the first time in history, we have a single instrument that outputs three simultaneous global maps: a density map from total brightness, a temperature map from the spectral smearing, and a velocity map from the Doppler shift. This is the Rosetta Stone of heliophysics. With these three maps, we can finally test the theories. If CODEX sees a gradual rise in temperature and smooth acceleration, it validates the wave turbulence model. If it sees bursty structures, hot blobs, and impulsive jumps in speed, it validates the Interchange Reconnection model. Most likely, it will find a complex hybrid, revealing that the sun uses different engines for different types of wind. Now, let's talk about the engineering, because building this wasn't easy. The International Space Station is actually a terrible place for a telescope. It orbits Earth every 90 minutes. That means 16 sunrises and 16 sunsets every single day. The instrument cycles between scorching sunlight and freezing darkness constantly. This creates thermal snapping, where metal expands and contracts. For a precision optical instrument where alignment is measured in microns, this is a nightmare. The CODEX team had to design a robust thermal control system with active heaters and specialized insulation to keep the optical bench perfectly stable. Furthermore, the ISS vibrates, astronauts run on treadmills, supply ships dock, and robotic arms move. To keep the occulter disk perfectly aligned with the sun, CODEX uses a high-speed auto-guiding system. It has a separate guide telescope that locks onto the sun's limb and drives a fast steering mirror to compensate for the station's jitters in real time. This mission is also a prime example of international synergy. CODEX does not work alone. It is the bridge between two other major NASA missions, the Parker Solar Probe and Punch. Parker Solar Probe is a daredevil. It dives deep into the corona, touching the plasma. But it is an in-situ spacecraft. It's like a blindfolded person sticking their hand out of a car window. It knows exactly what the wind feels like right there, but it can't see the storm it's driving through. Punch, a future mission, will be a wide-angle photographer looking at the solar wind as it moves out toward Earth. CODEX sits in the middle. It sees the plasma before it hits Parker Solar Probe. It sees the birth of the structures that Punch will track later. This allows for connection science. We can spot a blob in CODEX, calculate its speed, predict when it will hit the Parker Solar Probe, and then verify our remote measurements against the ground truth of the probe's sensors. So why does all of this matter to you? Why should we care about the temperature of the corona? The answer lies in space weather. The corona is the muzzle of the gun that fires coronal mass ejections at Earth. These are billion-ton clouds of plasma that can slam into our magnetic field, causing geomagnetic storms that can fry power grids, disrupt GPS, and endanger astronauts. Currently, our ability to predict the arrival time of these storms is based on guesswork regarding how much they accelerate. CODEX will give us the actual physics of that acceleration. By feeding CODEX data into our computer models, we can narrow down the arrival window of a solar storm from 12 hours to just a few hours. That gives power grid operators crucial time to prepare and protect our infrastructure. But beyond the practical, there is the profound. The sun is the only star we can study up close. But there are billions of stars like it in our galaxy. Many of them host exoplanets. We know that stellar winds can strip the atmospheres off of these planets, rendering them uninhabitable. By solving the physics of the solar wind with CODEX, we are learning the universal rules of star-planet interaction. We can apply these findings to red dwarfs like TRAPPIST-1 or Proxima Centauri to understand if life could survive there. We are moving from an era of description to an era of calculation. We are no longer just drawing pictures of what the corona looks like. We are calculating what it is. As CODEX streams its gigabytes of data down to the operations centers in Maryland and Korea, we are peeling back the layers of blinding light to reveal the hidden machinery of our star. The ghost in the machine is finally being exorcised by the rigor of data. That's it for this deep dive into the CODEX mission. Thanks for listening to G Fun Facts Online.